Question 7 involves some symbolizing. So now let's write up a symbolization key for this one. So I've got I play soccer or basketball. Whoever plays soccer also plays basketball. So I can sort of see that I'm going to be wanting whoever, I'm sort of going to be wanting to be quantifying over people. So I'm going to make some predicates which are talking about this person plays basketball or this person plays soccer, and then my names are going to be names of people. And the only person that's really involved is me. So I'm going to write I, and that can be me. And playing soccer, how about SX can be X plays soccer, and BX can be B plays basketball, X plays basketball, sorry. And that is all that we need for for symbolizing this argument. So let's get started. The first premise is I play soccer or basketball. So I'm going to write that as I play soccer or I play basketball. And the next one is whoever plays soccer also plays basketball. So we can sort of rephrase it as anyone who plays soccer also plays basketball. So if someone plays soccer, then they play basketball. So for all X, if X plays soccer, then X plays basketball. And the conclusion is therefore I play basketball. That would be BI. And right, so we have to negate the conclusion to start off with, because we're trying to find out if this argument is valid. I'm looking at my universal here, and I can tell that the only thing I'm going to be applying, the only sort of relevant variable here is I. So I'm going to apply I to line 2. So SI arrow BI. And so I've applied this to the variable I, and that gives me line 4, which came from line 2, using the for all rule applied to variable I. And right, I've got this is a branching rule over here, and this one's also a branching rule, so why don't we start at the top, SI, BI. So line 5 comes from line 1 through the OR rule, and I can tick that off. And do I have a contradiction? Yep, I do, because I've got negation of BI here and BI over there. We can cross that off. And now let's deal with line 4. So that's also a branching rule, negation of SI or BI. And so I can tick that off. Line 6 coming from line 4 through the arrow rule. And I've got a contradiction over here, SI and its negation, and over here as well, BI and its negation. So there are no open branches, and that means that means that there are no counterexamples, so this argument is valid. B says, I am only friends with someone if he is friends with them too. Therefore, I am friends with him. So what are the names in here? I've got I, so that's going to be, I can be me. And yeah, well, there's also he and him. And so that's going to be another name. Because in this context, it's clear that he isn't being treated as a variable like them or one, but it's talking about a specific person referred to as him. So what do I have any predicates? Well, I've got friends with, friends with, and friends with. So I'm going to say if x, y is x is friends with y. Right, so let's try summarize this argument. So I am only friends with someone if he is friends with them too. So we've got an only if over here. So I am only friends with someone. So let's say someone over here is not saying, you might think that that's an existential because it has the word some in it. But that's not sort of what this sentence means. It's only an existential if it's saying there exists someone. And over here, it's not got the sense of there exists someone for whom a statement is true. It's rather, I am only friends with someone. It's sort of saying, applying to anyone, I'm only friends with that person. So it's actually going to be a universal that we want over here. So for all x, I'm only friends with them if he is friends with them too. So I am only friends with x. We can go, I am friends with x, arrow, he is friends with them too. So he is friends with x. And the reason I've got the arrow around this way is because of the way that you translate the only if. So this happens only if that happens. Sorry, the first one happens only if the second one happens. I am friends with someone only if he is friends with them too. So there's only one premise, and the conclusion is therefore I am friends with him. So X is friends with Y, I am friends with him. And so those are the only two things in my tree, and I'm trying to find out if the argument is valid, so I'm going to negate the conclusion. Let's put that a bit closer so I don't forget about it. So I've got a universal here, and I have to apply that. I can already see that I've got two names in the tree. I'm going to have to apply that to both of the names. So let's go for let's apply it to H first. I've got FIH arrow FHH. So line 3 comes from line 1 using the universal rule for the variable h. So I can write over here that I've applied this to h. And now I'm going to do the arrow that I've got in front of me in row 3. So that's the branching rule, negation of, sorry, I think I may prefer to just apply this to I as well before I do any other branching, just for simplicity. So let's do the same thing for the variable I. If I arrow FHI. Now I've applied it to I. Now now I've applied this to all of the names in the tree, so that's good. That one is fully decomposed with all the names that we have so far, at least. So I've got line 4, which came from line 1 using for all with the variable I. Right, so I'm going to have to deal with these two arrows, which are both branching rules. So let's do row 3 first. That gives me negation of the antecedent and the consequent over there, so I can take that off. Line 5 coming from line 3 using the arrow rule. And do I have any contradictions or branches I can close yet? No, I don't. Nothing is contradicting. So I'll apply, I'll do line 4, line 4's arrow, negation FII, and FHI, negate same thing on the other branch, FHI. So I had to do that rule on both of the open branches. So line 6 came from line 4 using the arrow rule. And now I really have decomposed everything, and I can see if I've got any contradictions. So over here, I've got FIH, but I've got the same thing over here, so there's really no contradictions on this branch, for example. So I don't even really need to check the other branches because I found one of them where it is, yep, I found one of them which is an open branch. Now, is it also a complete branch? Yep, it is, because I've decomposed all the formulas, and I have to always check the universal formulas. Have they been decomposed with all of the names that appear on that branch? Yep, because the only names appearing on this branch are I and H, and I did that line for both of them. So that's good. So now I've found a counterexample, which makes this argument invalid. Now let's write out a model for this counterexample. So what information do we have? We have I and H are our variables, and for fxy I can read off that fii is false, fih is false as well, fih, and this also tells me that fih is false, so that gives me the same information. So these two could be anything, so why don't I make them, I'll make them both zeros. So yep, let's test this counterexample. This model, I'll just write the domain is I and H. Let's test this model with the partial predicate truth tables to see, yeah, to prove that it stacks up. So the premises were, the premise was all x, fix, arrow, fhx, and the conclusion was fih, and I'm going to put the negation there. So now I have to write down, I can see there's no x's and y's here, there's only the variable x. So I only need a column for the variable x over here. And the possibilities for that are I and H. Let's fill in some rows. Let's do this end one, it'll be easy. FIH was 0, so so I don't really need to do for both of those. That's 0, so the negation of it will be 1. And let's make sure that the first formula has the value 1 as well. So over here, fix, if x is I, then that's fii. Fii is 0, and fhx, if x is I as it is in this row, then that means we're looking at fhi. Fhi is 0 as well. So 0 arrow 0 is 1. Now let's do the row over here. Fix means fih, which is 0, and fhx means fhh, which is 0, and 0 arrow 0 is 1. So I've done those two columns. Now we have for all x, is the following true? Well, x ranges over I and h, so I'll group them like this, and it is true in both of those. So the value over here is 1. So here we have that the premise is true and the negation of the conclusion is true, which means the conclusion is false. So this counterexample, this model that we had, is a counterexample to this argument, and it shows that this argument is invalid. And finally, this one says that, this one says no scientific theory is certain. So, it's false to claim that if climate change isn't certain, it's not a scientific theory. This one has quite a long conclusion, and it seems to have just one premise. So let's see what we need in terms of objects. So it says no scientific theory is certain. It's false to claim that if climate change isn't certain, it's not a scientific theory. So it looks like the things that things can be are being certain or being a scientific theory. So let's call Sx can be X is a scientific theory, and Cx can be X is certain. And what names do we need? Well, we're talking about climate change in particular, so let's call that C. C can be climate change. And that will be all we need in our symbolization key. So let's symbolize this argument. The premise says no scientific theory is certain. I'm going to write that as for all x, if it's a scientific theory, then it's not certain. XX, SX, arrow, CX. Sorry, not CX. If x is a scientific theory, then it's not certain. And my conclusion is, therefore, it's false to claim that, and it talks about this whole rest part. So therefore, it's false to claim that if climate change isn't certain, it's not a scientific theory. It's like an if then, so I'm going to use the arrow. If climate change isn't certain, so not C for climate change, then it's not a scientific theory. Then not SC. Alright, so I'll set up my truth tree, and we're testing an argument for validity, which means we need to negate the conclusion. Alright, so first off I can get rid of this double negation. So I've got not CC, arrow, not SC, and that came from line 2 using the double negation rule. And now I've got line 1, I've got a universal, and there are no existentials in here. There are no, I can sort of tell that there's not going to be any more, since there's no existentials and no negations of universals, there's not going to be any more names other than what we've already got, being C, popping up here. So I'm going to go ahead and apply the universal because I can sort of tell that we're only going to be dealing with C here, so I might as well apply that at this stage. So I've got SC, arrow, not CC, and that has been applied to C. So line 4 came from line 1 using the for all rule with the variable C. And so now I've got these two arrows, so I'll just have to decompose them one by one. So let's do line 3 first, negation of CC, negation of CC, and negation of SC, and that is line 5 coming from line 3 by the arrow rule, and line 6 I'll get rid of my double negation, and that came from line 5 in the double negation rule. And I don't see any contradictions yet, so I'm going to decompose this the second arrow over here. So I've got negation of SC and negation of CC, and apply the exact same thing on the other branch. Because you remember, if I have a rule and I have 2 open branches, then I have to apply that rule to all of the open branches. Line 7 came from line 4 with the arrow rule, and we'll take that off. And do I have any contradictions or branches that I can close? Well, I've got this one here. where these two contradict, but the other branches seem to be fine. So I'm going to pick one that is open, and I'll check that it's complete. So this is open because there's no contradictions on it all the way up to the top. And is it complete? Yep, because all of the complex formulas have been decomposed, and what that means for the universal one to be decomposed is that it's been applied to all of the variables, all of the names in the branch. So I can see it's been applied to C, and that's the only name in the branch. Yep, so that means that this formula is decomposed. So this is an open branch that is also complete. Right, so that means that this argument is invalid because we found a counterexample. So let's flesh out that counterexample and test it with partial truth tree. So what's in my domain? I've got just C, and the two predicates that I have are Sx and Cx. And how do they apply to C? Well, Sc, I can see over here is false and Cc is true. That is the model that gives me the counterexample. Now let's check that the premise is true and the conclusion is false. So I'll write for all x, Sx arrow negation Cx, and negation of negation Cc arrow negation Sc. And the only variable that is mentioned in either of these formulas is x, so we only need one column for x. And how many rows do I need? Well, there's only the variable c, so I only need one row being c. Let's do the second one because it'll be a bit easier. The value for cc is 1, looking at my table over here, and the value for sc is 0. So the negation is 1, and this one's negation is 0, and so 0 arrow 1 gives me 1, and so the negation of that is a 0, and the negation of that is a 1. So I've got the negation of the conclusion being true, or in other words, the conclusion being false, which is what we're looking for. And over here, negation, let's look at Sx. So x is C, which means that Sx is Sc, which is 0. And Cx will be Cc, which is 1, sorry, and its negation is 0. So 0 arrow 0 is 1. And for all x, is the arrow's value 1 for all values of x, for all the rows? Well, yes it is, because there's only one row, and on that row it is 1, so the value for all x is 1. We have the premise is true and the conclusion is false, or the negation of the conclusion is true. That shows us that this is a counterexample to this argument.